So we are at the last talk of the week, and this is a great pleasure to introduce George Linardopoulos, who will tell us about string integrability in brane-deformed holography. Please.
Yeah, you can hear me. Yes. So, great many thanks to the organizers for organizing this wonderful meeting and conference, and also for having me here. It's a pleasure to be in Berlin and be able to present my work with, Kostya last February. Started off with Kostya Zarembo last February and continued also, this one, and this is this February. Extended the results of our first papers. And my talk title was suitably adapted to the keywords of this conference. Contains the words integrability and deformations, and this is probably also contains the word dualities, holographic dualities. So here's the plan of my talk. I'm going to start off with an introduction, and then I'm going to pretty much repeat what is known about string integrability within ADS-CFT. And finally, I will describe or say closed string integrability in ADS-CFT, or periodic, closed string integrability in ADS-CFT. And I will, in the final section, I will describe open string integrability, or what is known as also brane integrability in ADS-CFT, de-brane integrability in ADS-CFT. And let me first describe what's the setup of this, that this work belongs to. And the setup is boundaries and defects, the physics of boundaries and defects, which is, of course, so broad. Boundaries and defects are part of real world, Realphysik, say in German. And, of course, it's based on the fact that the real world is really imperfect, has imperfections, and many different point of views, many different impurities, domain worlds. And this is what we live in. And of course, boundaries are really physics. But of course, what I'm going to be focusing on is some formal aspects of defects. And these are, of course, arise, as we all know, or probably most know very well, within holography and the ADS-CFT correspondence, where, of course, we have a boundary theory, which determines and is determined by a bulk theory. Of course, string theory contains open strings, which were, of course, have their endpoints. Can be closed, of course, but the open strings have their endpoints on d-branes, which are themselves dynamical objects and give rise to a great many interesting field of d-branes within string theory. And of course, quantum entanglement, maybe we have a system that is separated in two or more subsystems, and there is a surface or a defect that separates these systems. And what we are interested in is find how the degrees of freedom actually are reduced and give rise to entropies, etc. And of course, there are then applied aspects, and probably the ones that are relevant to the present work is the physics of statistical systems near surfaces, which is completely different, of course, than statistical systems near, not near surfaces in the bulk. Critical exponents are completely different near surfaces. And also topological materials. These materials are known to have some topologically protected modes on their boundaries, on their surfaces. And topological insulator, of course, are prime examples of topological materials. And then also out of equilibrium systems and quantum quenches have been shown to also be relevant to boundaries and defects in the so-called scattering picture, etc. And then, of course, natural boundaries and defects permeate all branches of physics. And this is the general setup. But now I will be focusing more and more to my to the field that I will be exploring. And this has to do with boundaries and defects within quantum field theories and very special types of quantum field theories, which are conformal field theories. And this field is probably owes its beginnings to Cardy, who in 1984 studied, motivated of course by the physics of statistical systems near boundaries, studied the codimension one boundaries within a defect conformal field theory. A conformal field theory in d dimensions. And in fact, it's very clear that this boundary, say at point z equal to 0, breaks translation invariance, and then this gives rise, beginning with a Euclidean conformal group, the system with a boundary respects a subset of this Euclidean conformal group, namely conformal group in one dimension less. And of course, as I anticipated, the presence of boundaries completely alters all that we know about and we loved about CFT correlators. We have a completely new set of conformal data in this case. And of course, the study of higher codimensional defects and the use of them to bootstrap both the original and boundary CFT are part of the conformal bootstrap program. And certain types of defects can really be roughly described by that type of action, which contains, of course, the d-dimensional action, and if it's a con-dimensional one defect, it also has degrees of freedom on the boundary, which interact and interact with the bulk theory. And this is precisely the type of defects that we are going to see, but of course in a holographic setup. And I'm interested in defect CFTs that are holographic. That is, they have a dual, which is a gravitational dual, or a string theory dual. And the prime examples, of course, are the of holographic dualities, which I'm going to be deforming by means of d-branes on the string theory side and codimension one walls on the dual theory side. Is the ADS-CFT correspondence, which is of course known to be quantum integrable in the planar limit. And secondly, also the ABJM duality in the version that involves string theory on ADS4 cross CP3, which is again quantum integrable in the planar limit. And yes, these two theories are my prime focus, and I'm going to be examining the string theory side, where I will be inserting probe d-branes and studying the integrability of strings that end on these d-branes, and eventually showing that the boundary conditions for these strings are integrable. And so let me first go through very quickly these theories. Of course, we have n equals 4 super Yang-Mills. This is a conformal field theory having exact superconformal symmetry. And of course, as I said, this is quantum integrable in the planar limit, and this integrability was first manifested in the spectrum of scaling dimension by the work of these people, Minahan and Zarembo, Beiser, Christensen, and Staudacher. And of course, integrability solves the spectral problem of n equals 4 super Yang-Mills. And of course, we extrapolate to the whole theory and say that this integrability should be present in all the theory, or not only the spectrum, but and the computation of the theory's observables in the planar limit is currently underway. And of course, this also allows us to check the validity of this correspondence in the planar limit. And the same, what was that? I forgot to say, maybe relevant to this work, half-BPS boundary conditions in this theory was studied by Gaiotto and Witten. And so now the same is true for ABJM theory, which is again a gauge theory with conformal symmetry, and well, much more maybe maybe rich potential structure with sextic and mixed quartic interactions. And again, this was shown to be integrable with regard to its spectrum by Minahan and Zarembo again. And again, there is a solution of the spectral problem of this theory by quantum spectral curve. So much for the gauge theory side of these theories, and now I'll be going to the string theory side, which has also been shown to be integrable in the planar limit and also in the tree level or infinite coupling, classically integrable, that is. And I'll go through the procedure because it's going to be the basis for what I'm going to be doing with open strings. So first one has to define what is strings in this background, and these backgrounds actually, ADS5 and ADS4. And this crucially depends on the fact that these backgrounds, both of these backgrounds can be written as products of cosets. Which themselves then, I mean, this product is itself the bosonic sector of a higher supercoset. And this was done famously in this work, which built, of course, on earlier work on writing Green-Schwarz sigma models as cosets on flat space, and this famously showing that this reproduces the Green-Schwarz action. And the same is true, of course, for ADS4 core CP3, can be written as a coset, which is itself a bosonic sector of a supercoset. And these supercosets are known to be semi-symmetric spaces, what we call semi-symmetric spaces. And these semi-symmetric spaces have been known to be integrable. Sigma models that describe Green-Schwarz superstrings. And this is the Green-Schwarz model that we will be studying. I mean, people who worked on integrability of classical strings in ADS-CFT related backgrounds. And of course, these are, let me explain, maybe, of course, many people have really created all this work. And of course, I just mean to remind certain people who are not really working on this area. And so these are the so-called currents, which are defined in terms of supercoset elements, G. And of course, the fact that these backgrounds are really semi-symmetric means that they afford a Z4 decomposition. So this part is of course, this part of, so the semi-symmetric cosets are spaces which have a subset which can be invariant under a discrete Z4 automorphism, omega. And this omega really pertains to this zero bosonic part of the subset of the supergroup. And of course, this is what it, this automorphism is the one that endows the supercoset with a Z4 structure. So semi-symmetric space, symmetric spaces, on the other hand, are just bosonic spaces that afford the Z2 decomposition. But now, once we have the fermions, we have two more, components in this decomposition, which, of course, are carried out by means of a discrete automorphism omega, and I provide the details of this automorphism in here. And of course, we also have a parameter matching between the two sides of this duality, which allows us to write the corresponding tensions in terms of the 't Hooft coupling constant. And so what did I say? Yeah. So these currents, of course, let me go to some formal facts, as I say. So this current, of course, has a vanished curvature. It's very easy to differentiate this relationship and see that it satisfies this equation. And then by using the equations of motion that arise from this sigma model, one can show that there is a flat Lux connection, which is given by this formula here. And flatness means that it satisfies this equation. Again, a flatness condition. And X is the so-called spectral parameter. Now there exists a more convenient form of the current, which is so-called the fixed frame current. The one that we just show here is the so-called moving frame current, big J. Small j is all left current, which is given in terms of this transformation. And of course, this again is still flat, but it gives rise to a more convenient form of the Lux connection, which does not contain the invariant subset, the invariant, yes, so bosonic element. And this is what was famously used by Benham, Polchinski, and Royban to prove integrability of these strings. And let me go through their argument very quickly. So the argument of proving integrability, of course, we know the classical Liouville integrability. We need the number of conservation laws or charges, which is equal to the number of degrees of freedom of a theory. And then these conservation laws can be inverted and typically provide a solution to the equations of motion of classical theory. But now, of course, we have the field theory here that is infinite degrees of freedom, and so we need an infinite hierarchy of conservation laws, which ideally they can be inverted and give solutions. So this is exactly what is meant by integrability and solvability. And in order to actually construct these conservation laws, we need this object here, which is known as the monodromy matrix, which is just the holonomy of this Lux, this component of the Lux connection, of this fixed frame Lux connection. And it's very easy to see how this leads to an infinite set of conservation laws. We just need to differentiate this monodromy matrix. And then by using also the flatness of the Lux connection, which is very crucial, of course, and equivalent to integrability, we arrive at this formula. And then, of course, we have to use take the trace of this quantity and use the fact that we impose that is periodicity, the strings, that is closed strings. And one can find probably the first charge in this conserved hierarchy. And of course, higher charges, as it was also stressed in previous talks, can be generated by taking powers, appropriate powers of this quantity, this transfer matrix now, because it's just the super trace of the monodromy. And the charges, of course, can be obtained typically by expanding this monodromy matrix around appropriate values of the spectral parameter, and one identifies each of these expansions. So in the bosonic case, so let's take the fermion part to 0, so we are only left with J2 currents. We can identify this with charges, and one can really read off the charges from this relation and appropriately show that these charges are conserved. And this is, of course, the weak sense of integrability. Probably one needs to also have independence of these charges. We cannot really generate infinite charges, and they cannot be really the same charge. They have to be different, and so they have to Poisson commute. And there is very nice work actually showing this independence of the charges. And so much for string integrability. Now let me go to brane integrability. And but first let me summarize a bit. And of course I have to define the branes and I have to define everything. But so holographic defect conformal field theories were first realized in the context of the ADS-CFT correspondence by Karts and Randall in 2001 with a completely different motivation. In fact, the brane-deformed holographies, and these holographic CFTs were actually deformations of the dualities, the ADS-CFT duality, ADS-5 duality that I showed you before by brane. And this was done by Karts and Randall in 2001. And of course, I already discussed the boundary conformal bootstrap program. Another technique which can be applied to the study of holographic defect CFTs is integrability, of course, which was introduced to these setups by Deleu, Christensen, and Zarembo in 2015. And this led to a systematic calculation of the defect data. And moreover, recently, well, in 2020, localization methods were also put forward in these setups, and they permit to carry out precision tests of the dualities that I'm going to be showing you in the next slides beyond perturbation theory. So let me go first through the Kac-Randall system, which will define the boundary conditions for our strings. And then I will, of course, try to show the integrability of strings. And first, remind you that ADS type 2B string theory that shows up in the right-hand side of the, as I showed it, and of ADS-CFT duality, is encountered very close to a system of n-coincident D3 branes. And these D3 branes are, of course, heavy objects which curve the space-time around them, and they give rise to a singular space-time. And ADS5 crosses 5 and 2B string theory are encountered very close to the throat of this geometry. And the D branes extend along these three directions. And now what Kac-Randall did, they inserted the D5 brane at the point x3, x7, 8, 9, 0. That is, these are 0 and this is 0. Of course, this is the flat configuration, but maybe it's very, very illustrative of what I want to say. And in fact, one can show that the geometry of this probe-brane, it's just a single D brane intersecting the D3 branes, or equivalently, yes, I will say that probably in the following, a D5 brane inside ADS5 crosses 5. And one can show very easily that this brane will have a geometry of ADS4 crosses 2. So this is the setup, the holographic setup that we get. On the bulk theory side, we had 2B string theory in ADS5 crosses 5. But now we have a probe D5 brane of ADS4 crosses 2 geometry, which bisects this the bulk. And this, of course, corresponds to a dual CFT, a defect CFT, which was initially, of course, this part was dual to n equals 4 super Yang-Mills with SUN gauge group, and this part the same. But now we have also this, the projection of this D5 brane to a wall, 2 plus 1, codimensional 1 wall in 4 dimensions. And yes, and De Wulfe, Friedman, and Oguri studied this. So of course, I showed you the Lagrangian of n equals 4 super Yang-Mills, but now this immediately implies that there is another conformal field theory on the superconformal field theory on the defect that interacts with n equals 4 at 0. Yes, and this was studied by De Wulfe, Friedman, and Oguri, and also led to study of spin chains, etc., in the defect setup by De Wulfe and collaborators. And because of the defect, of course, the symmetry of the system is lowered. From bosonic symmetry is lowered to SO32. Of course, this means that we break the conformal translations, and the superalgebra of course is halved, is OSP44. So it's a half-BPS defect in this case. But one can also consider adding k units of magnetic flux through the two-sphere of the brane. Remember, the brane had the geometry of ADS4 crosses 2, and we can introduce k units of flux. And this means, of course, by energy conservation, that exactly k of the D3 branes will end on the D5 brane. But one can show by going, of course, to the DBI analysis, etc., that the geometry will still be ADS4 crosses 2, and it will be stable. So even if k is 0 or k is non-zero, this geometry of the brane is stable against perturbations. And moreover, the embedding of the D5 brane will be described by these equations here, where this is actually fluxed in the units of inverse square root of lambda. And of course, the metric of ADS5 is written here for completeness. And the two-sphere, of course, is parameterized by these coordinates. Yes, and of course, as I said, we now have a tilted D5 branes, where in the case A, alpha different than 0. The brane is tilted now. And on the S5 part, we have a D5 brane, which is a stable to sphere. This sphere is usually, sometimes it can be unstable towards flipping off the sides of the sphere, but this has been proven to be very stable in the presence or in the absence of flux. And now the setup, the holographic setups in the presence of flux is this one. As I said, because of energy conservation, K of the D3 branes have to end on the D5 brane. And this, of course, induces a decrease in the gauge group rank on the left-hand side. But still on the right-hand side, we have the same setup. And this has been shown again by Katz and Randall to be equivalent to the development of a non-zero vacuum expectation values for the fields of n equals 4 super Yang-Mills. And one can use this fact in order to compute correlation functions as Higgs condensates of gauge invariant operators of n equals 4 super Yang-Mills. And by introducing, of course, matrix product states, one can compute beta state overlaps and take closed form determinant formulas, which of course are a manifestation of quench integrability. So there is the notion of quench integrability, which I don't go to go in, but this concerns the dual gauge theory side. And so one of the manifestations of integrability is the fact that we can really write closed form formulas for the CFT data. That is the structure constants of one-point functions. And of course, yes, this is the question that was just answered. One develops integrable quench criteria that apply to the gauge theory side, and one can indeed show that they are satisfied. So we expect this system to be integrable. Yes, much as n equals 4 dual to 2B string theory is. But of course, as I showed you, 2B string theory was known to have integrability, classical integrability, and we would like to complete the picture by showing classical integrability also in the defect setup. This is, of course, again, the D2 D4 brane system, which pertains to the ADS4 cross CP3 duality. Again, we have D branes along D2 branes this time, and we have an intersecting probe T4 brane along these directions here. And the geometry of the probe brane can be shown to be ADS3 cross CP1 in the non-flux case, but also in the flux case, as I will say. And this is the geometry of ADS4 cross CP3. One can really very quickly see why the geometry of a probe brane will be ADS3 cross CP1. This is the geometry of ADS4 cross CP3. One can set these angles in this metric to 0, and immediately these terms cancel, and then what remains is the metric of this. And the same, of course, went through for the D5 brane, but this is a very sketch of the DBI, formal DBI proof of this geometry. And yes, this is of course, I have to say that CP1 is nothing but a two-sphere, again. And as I said, we can introduce flux to the system as well in the CP1 or S2 part. And again, D2 branes will terminate a number of D branes. Q, which is proportional to this flux, will terminate on one side of the D4 brane. And the embedding of the D4 brane will be very similar to the one that we saw before, but in a probably more complicated background, which is ADS4 cross CP3. And again, we have the same geometry for the D4 brane. We have a tilted brane in ADS and a CP1 brane inside CP3. And again, this is the setup for the holographic setup. that was recently set up by Christensen, Vuez, Zarembo, and the recent work by Gombor and Christensen showed that one can also write down closed form determinant formulas in this theory as well. Smoking gun of integrability of the system. And as I anticipated, we want to study integrability on the strongly coupled side of these dualities, namely on the string theory side, which of course entails open strings. And ending on these D branes that I showed you, having these embeddings that I showed you. And so in general, so the general question is, of course, whether opening the boundary conditions of integrable. So if we have boundary conditions which are closed and unintegrable, and we suddenly open them, is integrability of the strings preserved? And the answer is no, and we already have backgrounds which, even in this setup right here, we have backgrounds where certain non-supersymmetric D branes are either known to break integrability of ADS5 CFT4. But there is another setup, of course, non-supersymmetric that we don't really know. It might preserve integrability. But we know examples that break integrability. So the question is whether we can still have integrability in these theories. But the signs, of course, are very positive. And yes, and they go after the fact that we have already found, people have already found, worked out closed form determinant formulas. And as I said, there is, what's this? Yes, one can use, of course, the conformal data to solve the theory, but I want to say about integrable quench criteria, which I briefly mentioned previously, which, of course, are formulated by means of the parity of charges of the spin chain of the theory, that is, describes the dilatation operator, etc. So if this actually annihilate the boundary state, so then there is a nice criterion by Piroli, Posgay, and Vernier, which says that the quench or the defect CFT seen as a quench, if we could weak rotate it, is integrable. And this has been shown, of course, for both of these systems. That, well, recently it was shown also for the ADS4 system. And of course, as I said, closed string, we just show that, seen that they are integrable, and the question is what happens if we open the strings. And of course, there is, I should probably highlight the work of Dekel and Noz, which actually proved the classical integrability of both of these systems, which is yet another indication that these systems are integrable, but for zero flux. And my work with Kostya is that we generalized this work to system having non-zero flux on the D brane. And now this brings me to the topic of D brane integrability. And I first have to remove the fermions. So I only consider bosonic strings. And the action, of course, that the string sigma model on either ADS5 cross S5 or ADS4 cross EP3 in the absence of fermions reduces to the Polyakov action. And here we also have a flux on the boundary, which couples to the string action by means of this boundary term. And one can vary this action.
Sorry, can I just?
Yes, yes.
I missed. Why did you get rid of the fermions?
In order to make my life easier. Okay. It's much more difficult. I can comment on the fermions because, yes, it's, yes, I'll probably mention that later, yes. It's much easier to study, of course, yes, the case, but it would be, of course, an interesting open question to study the fermions as well. And so if I vary this action, by demanding that the variations on the initial and final states vanish, I can arrive to this result, which says that the boundary conditions, and boundary conditions is this exclamation mark on the equal sign, this holds on the boundary, are Neumann-Dirichlet for the longitudinal coordinates of the string, these, and transverse are Dirichlet. And of course, I can translate immediately this set of boundary conditions. These are all the boundary conditions I can write for this system. And I can make this statement more precise. I can insert the parameterization, the embedding coordinates of ADS5 cross S5, and take these boundary conditions, which I don't know whether they are give rise to integrable string motion in these backgrounds. And of course, the same goes true for ADS4 cross CP3. I have these boundary conditions with flux, non-zero flux in here, in either ADS4 or CP3, and I want to know whether I can generate an infinite number of conservation laws, which I can invert and really solve my string, open string, bosonic string. And so in order to be able to answer the question, we need a construction which reminds us very much of the construction we had in the bulk. And this brings us to the work of Sklianin, which defined the double row monodromy matrix, which is built of the monodromies that we used in order to construct the hierarchy of charges in the bulk or for periodic boundary conditions, and a reflection matrix U, which takes the boundary into account. And this, of course, means that, so the charges, of course, you have to see this as, the charges are really, the conserved charges of the bulk are contained in these monodromies, but then the presence of this non-abelian structure in this monodromy, in double row monodromy, really eliminates certain of these charges, and we're left with less conservation laws. Well, we can, of course, have all the conservation laws in certain cases, but formally, we get less. And our task will be to find such a reflection matrix that will allow us to construct the conservation laws from this double row monodromy matrix. And the procedure is the same as before. We differentiate, and we demand that this matrix is constant. And when we do this, we arrive to this integrability condition, this exactly here, that must hold on the boundary, and this transfer matrix will be conserved. And of course, here is just the fixed frame Lux connection that holds in for strings in the bulk. And yes, and now. Yes, I can really, because we have, of course, this, we can plug this Lux connection into this formula and get a more precise form of the integrability condition, which is this one over here, which contains, of course, one term for boson, two terms for bosons, and two terms for the fermions. Let me connect with the work of Dekel and Oz. Of course, you see that if we include the fermions, we have more terms here. And this is already very difficult to solve, and you'll see that it leads to a complicated solution. But what Dekel and Oz did, they considered the no-flux case. In the no-flux case, this U matrix, this reflection matrix, is really a constant and does not depend on the spectral parameter, which means that this is zero, this side is zero, and these terms are really decoupled from each other, and they can be set to zero, and then easily be solved, even in the fermionic case. But in the bosonic case, and for generic U structures of U matrices or reflection matrices, we have to solve this equation. Which of course is dependent on the spectral parameter, and in fact U will turn out to depend on both the wall sheet time, tau, through the coordinates, and the spectral parameter. And and of course, the form of the U matrix in the bosonic of the reflection matrix in the bosonic case is just the block diagonal. One part for ADS and the other part for the compact space. And our job, of course, would be to find the U, which we will plug in this formula and make it and satisfy this formula upon using the boundary conditions that I showed you before. And then we can claim that the boundary conditions are integrable because we can really expand this matrix along, for the spectral parameter and obtain the charges as I showed you before. So let me go to the details. The details are that we know the coset element of ADS5, which is this one, and these are the P's and the D's and the K's are just the conformal generators in 4 dimensions. And one can use this in order to get the current and plug the current into this integrability condition and then search for a reflection matrix. And the reflection matrix is just the Deckel laws, constant reflection matrix gamma 3 plus a structure that depends on both the coordinates and the spectral parameter. And that was my work with Zarembo in 2021. And of course, as I said, that the K0 case, which K is here, if this is 0, then this is a constant matrix which fits perfectly with exactly the Deckel laws result. And the same goes true for ACE5. The parameterization is given by these nice quantities right here. We know again the current, and we can construct again these reflection matrices which are dynamical. That is, they depend on the coordinates and on time, and they depend also on the spectral parameter. And again, the zero flux case is the Deckel laws result. And ADS4 is very much similar to ADS5, and the reflection matrix is very much similar, and this part was really very, very straightforward. And again, Deckel laws had studied this case for Q equals 0, that is no flux. But of course, the CP3 parameterization is a bit more involved. And that was probably the non-trivial part in this paper. One can construct the charges, which are very much more complicated. But if one plugs it into the integrability condition and looks for a reflection matrix that satisfies it, one can find this reflection matrix here, which is not too complicated, but it works, and it really also reduces to the Deckel laws result for the zero flux. And that was more or less what I wanted to say. The conserved charges can be obtained, of course, by expanding the double row monodromy matrix at x equals 0. They are supposed to be independent, of course, since they are subset of the charges in the undeformed case. And but they are not going to be all of them are not going to be there. And of course, this work also may give rise to interesting other research directions. And so I have put the German version of thank you here. Yeah.
Thank you very much for the nice talk. Questions?
So you have written down these integrable boundary conditions, and I didn't understand if different choices are possible, and if yes, what would be a way to classify the full set of possible integrable boundary conditions?
So the boundary conditions were obtained from the Polyakov action with a boundary term when we vary it. So these are all the boundary conditions that there can be with this condition on the boundary. And these are all. And these are integrable. And yes, I don't know if so anything that can be written in this way gives rise to this is formally what's the interpretation of this result.
Yes,
and of
maybe-
course, this translates to these boundary conditions in ADS and the other, of course, in the ABJM.
Yeah, so for example, take ADS5, do we have other possibilities than what you have written in this slide or not?
There might be, of course, but if one can relaxes this kind of conditions, I don't know. Yes, there might be. Of course, there are the fermions, but if one relaxes these conditions, yeah. But you see, yeah. So formally, we want the boundary. How do we obtain the boundary conditions, right? We vary this action, and we end up with a boundary term, right? Because we have some partial integrations, we end up with a boundary term which has to vanish, actually. And if we set this type of conditions, then this boundary term would lead immediately to this boundary condition, bosonic boundary conditions. Yes. Now, one can ask, can we put some other boundary conditions which will lead to a non-vanishing boundary term? I don't know. Yes. This I haven't thought about it. But, yeah, maybe I need to say something about the fermions to complete the answer. So, of course, the fermions show up here in the integrability conditions. Of course, as you saw, the reflection matrices I got were really complicated. And of course, if one includes the fermions, they become much more complicated. But including the fermions really also modifies the bosonic part of the currents. Usually, the fermions are really, for example, we usually have this bosonic element. The fermions show up with an e to the x, the chi element, right? And then this, when one attempts to get the currents, one finds that there is a fermionic contribution to the bosonic currents. So not only this part will show up, but this part will have a fermionic component, which is bosonic, of course, but it's composed from the fermions. And one can really try it. Maybe I haven't examined this possibility. It would be, of course, very interesting to see if one can solve the full fermionic.
So maybe I have a somewhat related question. Can you just go forwards a few? Yeah. So this you have written down in coordinates, right? In target space coordinates.
Yes.
Do you have any idea if there is a form that you can write down that does not need you to explicitly reference target space coordinates or use generators? That maybe then you can generalize, including fermions, more easily. I don't know whether.
Yeah,
some deeper structure to
there
this.
is the question whether this classical reflection matrix arises from some quantum K matrix, right?
I'm asking a much simpler question.
And this is too complicated. So this part, this dynamical part, is too complicated actually to hope for somebody to really reproduce it in some classical limit of some quantum.
I mean, I think I'm asking a much simpler question. I just
okay.
want to write it as in terms of G rather than in terms of X's. And
in terms of G, yeah. No, well, we didn't. It would be very interesting. Yes, yeah. It would be interesting to actually try to write it. There could be some freedom in actually writing down this the dynamical part, but we didn't really go very much into it. And it would be very interesting, of course, if somebody came up with a simpler form for this, because of the reason also I explained.
Do we have any further questions?
Maybe just to clarify, can you go to the second slide? Sorry, the slide after this one.
The next one, this one?
Oh, no. So
Previous?
where you wrote down the U dot, yes, this one, thank you. So can you clarify why taking U to depend on time, that it gives you a boundary condition with a flux? Because if I look at this expression and it's telling me a relation between the sigma component of the current, from the second part that has to be 0, and then from the first part you get U dot and then the tau component of the current.
So your question is why we, for non-constant flux, we end up with dynamical reflection?
Yeah, why taking U dot to be non-vanishing, why it gives you a flux in the Neumann boundary conditions, basically.
Well, it's a fact of the calculus, actually. Dekel-Lenau's, well, if one tries, first of all, if one tries actually to solve these equations without a flux, one cannot solve them, really. And we tried, of course. That was our initial, we probably delayed writing down this paper because we at first we thought that the reflection matrices would be constants. And so we tried, of course, if this is 0, but still dependent on, you mean if this, if this is not, this is constant, but still dependent on the spectral parameter?
No. Yeah, simpler than, I'm thinking about the generalized Neumann boundary condition, which is a condition between a sigma, the derivative of the coordinates respect to sigma and tau, that it relates those two things. And here I just look at the second piece, which has to be 0 if I expand in the spectral parameter. And so I don't get a relation between a sigma derivative and a tau derivative. So I didn't understand why it would give you a boundary condition with a flux.
No, this is dot, right? This is tau derivatives, right?
Yeah.
And you mean here we have, yes, this should, this should, I think this should independently vanish, or there is some cancellation of sigmas. Yes. No, this takes place. But I cannot really recall all the details here. So you mean this, so let me rephrase it if I understood correctly. So you say you have these J sigmas here, which contain derivatives with respect to sigma, of course. And and the question is how I can make friends with this part, which only depends on derivative of tau. And the answer is that this part, well, one answer is that this part, let's see. Yeah, I don't remember very well, but yes. So if I end up, so one part, of course, would be that this cancels independently, right?
Yeah.
And then we still have a derivative here, and we still have all of that. But let me see. Is this all dependent on sigma? I don't remember very well. Yes. Yes. This is a good question, but it turns out that one has to use these matrices that we use, and I cannot remember very well what was the case for this. I cannot remember. Yeah, I don't think there is. Yeah.
We can talk about it afterwards.
Yeah, we can. Yeah.
The question originally is just because maybe probably previous slides you write down the generalized Neumann, which is a relation between the tau derivatives and the sigma derivatives.
Yes.
And so
That's also, yeah, that's also, yeah, you answered the question, yes, indeed. So that could also be, right. Indeed, so the boundary conditions really, yeah, that's the answer, indeed. So the boundary conditions really mix, let's see, where do they mix? So these are primes, but here you see they mix, dot and prime. And so we replace the derivatives in the sigma-dependent part with the tau derivatives, and then this couple with the other part, and they make 0. Yeah, that's a very good question, yes, a very, very technical question, but it's very interesting. So this couple, and indeed, that's the reason why they cancel.
Any further questions? So we will thank George in just a second, but before, don't run away after we do. So let's first thank George.
Thank you.